You're listening to People, Places, Planet, the official podcast of the Environmental Law Institute, a nonpartisan, nonprofit research and education institute making law work for people, places, and the planet. If you enjoy the podcast and want to support our work, consider donating at eli.org/donate.
Welcome back, listeners, to another episode of People, Places, Planet. I'm your host, Sebastian Duque Rios, and today we're kicking off a two-part series on geothermal energy, one of the most promising and often overlooked tools in the clean energy transition. As demand for reliable, always-on power grows alongside the rise of data centers and electrification, geothermal is having a moment, with new drilling technologies unlocking the potential to generate electricity in more places than ever before. In this first episode, we'll get a science and technology primer on how geothermal actually works and the new technologies emerging in the space, and we'll start to unpack the regulatory landscape that's shaping the industry today. Then, in our next episode, we'll be joined by a panel of guests to dig deeper into the financing, legal, and policy questions shaping geothermal's growth. To kick things off, I'm joined by Tom Lutken, a science fellow here at the Environmental Law Institute. Tom, thanks so much for joining me. Why don't you start by introducing yourself and telling us a bit about your connection to this topic?
Yeah, sure. Thanks, Sebastian. So my name's Tom Lutken. I'm a science fellow here at the Environmental Law Institute. I work on energy and energy transition topics and am one of the rare non-lawyers here at ELI. But my background's in energy and energy transition, like I said. So we first started talking about geothermal at ELI a little while ago, but once we sort of started to think about it much more seriously, we wanted to get a better understanding of current technologies, where the state of the science is, so that we could then talk about the state of the law and how it relates to the science.
Thank you so much, Tom, for that brief introduction. And maybe for geothermal, a lot of listeners might only know about geothermal from hot springs or the occasional news story from Iceland, which is a country that's renowned for its geothermal capacities, right? But what actually is geothermal energy and how does it work as an electricity source?
Yeah, geothermal energy kind of does what it says on the lid. So it's heat from within the earth. That heat comes from a combination of leftover energy from the planet's formation and ongoing radioactive decay in rocks that are deep underground. We often associate geothermal with things like hot springs or geysers, but those kinds of very visible activities, they're really just where that geothermal heat is making its way to the surface. It's a much larger, essentially worldwide resource that we can only see at the surface under unique conditions. Traditionally, those conditions have also determined where we can produce electricity from geothermal. Places like Iceland, California, and Nevada in the US, New Zealand, and Kenya, these all get a decent percentage of their electricity from geothermal power plants. Today, we really need about 4 ingredients, or maybe it's more accurate to say 3 ingredients and 1 condition to use geothermal for electricity. So first, you need hot temperatures, usually above 150 Celsius. Second, you need permeability, meaning that water can move relatively easily through the rocks. Third, you need water in those rocks. And then fourth, as the condition, you need all 3 of those things at a shallow enough depth so you can drill a well and not have it be too expensive or too unstable. Once you've got all those conditions, making electricity from geothermal involves drilling a well, usually several thousand feet down, depending on exactly where you are, and bringing that hot water to the surface. Once it's at the surface, the exact configurations can vary a little bit, but fundamentally, you're taking heat from the ground and generating steam to spin a turbine and make electricity. This is very similar to how a nuclear power plant takes heat and turns it into electricity, or how a natural gas plant does the same thing. Some of geothermal's biggest advantages are that it provides power nearly 24/7. It does so with very low greenhouse gas emissions, and it doesn't take up much space on the surface. Unlike wind and solar, geothermal systems can operate nearly all the time. The technical term for this is that they have a high capacity factor. That's your technical term for the day. And they provide electricity in a way that's very similar, again, to a nuclear power plant or a natural gas plant. Geothermal systems are also mostly vertical, so their plant footprint can be small per unit energy they produce. This is especially in contrast to something like a large wind farm or a large solar farm that can take up a lot of space. So you might be asking, okay, why aren't we all running on geothermal energy all the time? And the answer is that those conditions I mentioned earlier are rare. In the US, we really only have plants in the West, mostly in California and Nevada. Only about 0.4% of America's electricity comes from geothermal power today. And about 40% of that comes from one facility in California. It's called the Geysers, and we built that in the 1960s. So it's pretty rare to find the right conditions to use geothermal for electricity.
Thank you, Tom. And is risk a consideration here too? If the requirement is that temperatures are above 150 degrees Celsius, you'd presume that that means that these are areas with high levels of tectonic activity. Does that mean anything in terms of infrastructure risk?
It's funny, when you say risk, I have taken a lot of economics and I'm something of an economist myself. When you say risk, actually, the first thing that comes to my mind is financial risk. And that is the biggest one that people worry about when they build a plant like this. But to your point on physical risk, infrastructure, or other risks, it's more correlative than causal, I think, because most of the places where we have geothermal power today are in tectonically active areas. That's true. But most of that reason is because it is so much more expensive to get to the hot enough rock anywhere else that the price has functionally capped it to only really make financial sense in a place like Iceland, where there's already a bunch of geysers and volcanoes, or the parts of the United States like California and Nevada, where there are a lot of rocks that are hot that are close to the surface. So the east coast of the US, I think that you could eventually get to the right depth, right? And we can talk a little bit more about that in the other technology section. But in order to get to 150 Celsius, you only have to drill, I don't know, a quarter as deep in some place like Nevada and California. And at the end of the day, one of the big barriers in geothermal is for power generation, you are selling a thing that other technologies are competing with you to sell. And some of those technologies are pretty cheap. Like solar and wind have come down a lot in cost in the last 15 to 20 years. So trying to make a financial decision about where you're going to drill to make a geothermal plant is a huge filter to get through.
Awesome. Thank you, Tom. That's interesting. I think it's really relevant to some of the conversation that we're actually going to be having. So I think it's some great context for folks who will be listening. And to kind of move on a little bit, you were starting to hit at some of these technologies, and that goes to the point that there's a lot of different applications under this geothermal umbrella, right? And so for this episode, we're going to be focusing primarily on electricity generating geothermal energy. So how would you distinguish this kind from others, and what are some examples?
Yeah, that's a great point. Many applications for geothermal don't involve making electricity at all. I'll start with the lowest temperature and the shallowest depths for the examples. You can use technologies like a ground source heat pump, for example. These can be used for heating and cooling buildings. They're usually only a few meters deep, and they don't really extract heat from the ground. Instead, they take advantage of the stable temperature of the ground to more efficiently air condition or heat your house. Ground source heat pumps are basically a very efficient air conditioner and home heater wrapped into one. They're not adding energy to the electricity sector or the energy sector. They're just making it take less energy to heat or cool your home or office. So they're relevant for the energy transition, but they're not adding that energy. Going one level deeper, if I may, the puns are starting early, but going one level deeper, you can use lower temperature rocks that are almost always found at shallower depth in what we call direct use geothermal, where the heat is just used directly for things like heating your house, heating up a government building or offices. Warming up greenhouses is a fun one. Really things that just have to do with making things warmer. The temperatures needed for these direct use systems are lower. They're usually between 30 Celsius and up to that 150 Celsius threshold. Those are usually a few hundred to a few thousand meters below the surface. Those are a little bit simpler because you're really just bringing up hot water or hot fluid and getting the heat out of that instead of going to these extra steps to convert it into electricity. So again, those key differences are that electricity generation usually takes hotter rocks, which also usually means deeper wells. And making electricity means you have to have a big plant at the top of your well that converts that heat into electricity. Those added conditions mean that electricity generation has historically been, again, limited to these very specific places, although that is starting to change.
And so when we're talking now within the geothermal energy space, what are some of the emerging technologies that we're beginning to see? What are people referring to when they talk about these next generation or deep geothermal technologies?
Yeah, there have been some big, exciting developments in geothermal technology recently. We've gotten very good at some different drilling techniques and some other new developments that are allowing us to possibly use geothermal outside of those very limited geographical constraints. The first group of technologies, and I think the most widely talked about these days, is called enhanced geothermal systems, or EGS. This EGS system involves drilling into hot but relatively dry and sometimes pretty impermeable rock, and then creating artificial fractures. We do this through hydraulic fracturing to create those cracks, and then we inject water into the cracks. These EGS systems pump a working fluid, it's usually water or a mix of water and some other things, down into that network of cracks, and it permeates through the cracks, heats up, and then we pump it up the other side. This essentially creates kind of a man-made geothermal reservoir and can dramatically expand where geothermal could be deployed. This is the new technology that people I think are most excited about. You may have heard of a company called Fervo. They recently had a high-profile IPO a couple months ago, and Fervo is using enhanced geothermal. There are also closed loop systems. Sometimes people call these advanced geothermal systems, or AGS. These closed loop systems are basically just a series of drilled wells underground, and they don't involve any hydraulic fracturing. They just drill parallel wells and then connect them deep in the earth. I've heard people describe it as a big reverse radiator that pumps, again, a working fluid like water and a mixture of some other things sometimes. They pump that working fluid down to depth, the fluid heats up, and then you pump it up on the other side and you create electricity out of that hot water. And finally, the newest technology that is really still largely theoretical, that holds a great deal of promise and remains on the drawing board in a lot of places, is deep geothermal or super hot geothermal. We haven't quite coalesced on a single name for this because it uses some minor variations on the same general approach. Super hot geothermal is my favorite because it does what it says on the lid. So you go very, very deep. This is usually like further than 15 or 16,000 feet ground. And when you go that far down, you can get really high temperatures. Now we're talking like 375, 380 degrees Celsius. Now, this is important, and apologies for the chemistry lesson that's about to happen, but this is a really important temperature because water gets very weird when it's under that much pressure and at that high of a temperature, and it becomes what we call supercritical, which means it's behaving a bit like a liquid and a bit like a gas. The important part is that this supercritical water gives you a lot more power per unit volume when you bring it back up to the surface to make electricity. So drilling a few thousand more meters down sometimes can get you a big spike in electricity output.
That's really interesting, Tom. And the chemistry lesson is much appreciated. I don't think I've heard of the term supercritical in a while, but I do remember that from college chemistry. And just to clarify as well, so this technology of hydraulic fracturing that's used in enhanced geothermal systems, or EGS, is essentially fracking, like fracking in the way that we think of it in the oil and gas context. Is it similar to that, or is it kind of a different process?
It's pretty similar. And to be honest with you, I have had trouble finding a single answer that has coalesced from the range of answers I have found to this. You are doing a very similar job at the beginning. You're breaking rocks open, you're holding them open, they need to stay open, but you are doing a different job at the end, right? When you're pushing water through rocks and then maintaining the same amount of pressure underground, that is a little bit different from pulling oil and gas out of those rocks. So in large part, it is the same, right? You will do the same kind of breaking open of rocks, and the same technology for drilling horizontally is another big part of EGS that Fervo is doing a lot of work on. But it is unclear to me the exact degree to which hydraulic fracturing for an EGS system is similar or different from hydraulic fracturing for an oil and gas system. It probably depends on the exact rocks you're doing, how deep you have to go, and a few other factors.
Yeah, certainly makes sense. And it certainly seems like the kind of thing that, at least when it comes to considering this technology in the future and considering its potential environmental impacts, the kind of thing that merits further study. That is all really interesting, though. And it's really interesting to think about how much raw energy potential, at least, these technologies could hold if they're able to be implemented. And so I am curious, though, what are some of the technical limitations that these emerging technologies have? And are they being implemented anywhere today yet?
Yeah, that's a great point. These new technologies are all still emerging, though some are in more advanced places than others. Enhanced geothermal systems are progressing pretty rapidly. Their main unlock, if I can use a sort of a consulting term, but their main unlock comes from better hydraulic fracturing techniques, which we've been improving for many years now in the oil and gas sector. I mentioned Fervo earlier, which is a geothermal company that they've got a facility in Utah. And they, again, had this initial public offering a little while back, and they generated a lot of buzz. And they're actually generating electricity too. They're planning to start selling power to customers later this year. They've moved out of the experimental and into the sort of implementation phase. Hydraulic fracturing does, as you said, raise concerns about induced seismicity. This is basically causing small earthquakes because of the cracks that you made in the rocks and the pressure that you introduced into the rock formation, as well as environmental questions about groundwater. Additionally, geology can still limit EGS a bit. Not every place in the world has rocks at those temperatures that you can effectively make cracks in to make an artificial reservoir. So you'll get some geographies where it works better and some where it doesn't work as well. Advanced geothermal systems or closed loop systems avoid some of those issues that I mentioned with EGS. They don't employ hydraulic fracturing. But there's another geothermal company called Evor that's in the early stages of proving their closed loop technology can work. They're making good progress as well. The issue with AGS is that you have to drill a lot more of those parallel wells to get the same kind of power output. As water going through a single tube that just goes back down and comes back up, it has less chance to absorb heat than water that has gone through a whole series of cracks, small cracks in the rock between the two well tubes. Finally, and I think this is, again, sort of one of the most important limitations, and it applies to super hot and deep geothermal the most, but for all geothermal, is that drilling deep wells is expensive. Geothermal wells are usually wider than a traditional oil and gas well, and it makes them more expensive because the hole has to be bigger. And just making a deep enough hole in the ground can cost millions of dollars. One 2025 estimate showed that drilling activities are between 30 and 57% of the total cost to develop and install a geothermal plant. Those costs are coming down, but figuring out better ways to drill those holes in the ground will have huge implications since so much of the upfront costs are for drilling. One final company I'll mention that's trying to help with those high drilling costs is this startup called Quaise, which uses high intensity beams of light. They use millimeter waves, which are a little bit smaller than a microwave, instead of just a traditional drill bit to drill holes in the ground. This helps deal with a big downtime problem for very deep wells. Because it's so hot and the pressure is so high at these depths, any drill bit will inevitably start to fall apart. So you have to spend a lot of time pulling the drill bit up and replacing the drill bit and then lowering back down and then continuing to drill when you're doing such a deep well. The Quaise is an intriguing idea because they think that they could reduce this downtime by essentially blasting the rocks away with this beam to help reduce the stress on the drill bit and speed up drilling times, which would help lower those costs. That technology has probably among the furthest ways to go of the ones that we've talked about, but it's this super high tech and like innovative workaround for a very common problem that we see in all geothermal projects, which is, how much money and time it takes to drill a hole deep enough in the ground.
Yeah, the expensive drilling to sufficient depth is definitely a really important point and something that we'll be discussing very thoroughly in the following episode with our panel of experts. And that I hope our listeners will get to appreciate just how big of a role this factor plays in the ability to advance any geothermal projects, both in the US, but also in an international context as well.
What depth are we as humans used to digging to? Like, how does that depth pale in comparison to, let's say, your average coal mine or your deepest mine? Like, how do those things compare?
Yeah, I am not sure about the deepest coal and other mines, but compared to oil and gas wells, it's deeper, but it isn't like phenomenally more deep in the ground. The deepest oil and gas recovery is on that same order of magnitude. It's 10,000, 20,000 feet down. I guess the biggest difference is, for the most part, the rocks are different, right? For the most part, you're going into rocks that, necessarily have oil or gas in them. And those tend to not have the same heat and other conditions that you see. It's actually really funny. If you look at a map of the United States for like the best places to do geothermal and some of the not as good places to do geothermal, one of the not very good places to do geothermal is the Permian Basin in Texas. which is where all of the oil is in Texas, not all of it, but a whole lot of the oil in Texas is in this place that is also not very good for geothermal power. So we can drill holes this deep in the ground. The conditions in which those holes get dug are pretty different between oil and gas. So I think that's probably the biggest differentiator. I guess the other biggest difference between an oil and gas well and a geothermal well does come back to cost, right? The thing you're getting out of the ground in a geothermal well is heat to make electricity. And the thing you're getting out of the ground when you're drilling an oil well is oil. So per unit, you get a lot more money when you're getting oil out of the ground than when you're getting heat out of the ground, because the heat has to compete with a solar farm and a wind farm, and the wind and the sunlight are basically free. So that's another sort of big difference there. I'm pretty sure Deepwater Horizon was on the order of, 10 to 15,000, 20,000 feet below the surface.
Right. I'm just finding here that it drills to a maximum vertical depth of 30,000 feet.
Yeah, which is deep, right? So we can do it. Probably not the most sympathetic example I could have come up with, right? But that demonstrates that, like, we as an engineering species can drill a hole that far down. But I'm pretty sure the rocks 30,000 feet under the ground, under the Gulf, were not as hot. They weren't made up of the same materials. Maybe the rock wasn't as hard, things like this, because they had oil in them. And those two things are correlative. Oil doesn't usually pool up in granite bedrock. It usually pools up in things like sand, and sandstone, and things like this. So it behaves a little differently. But yes, we have dug holes in the ground that are steep, but the circumstances of how we dig them and some other factors do differentiate geothermal from the other wells dug.
Thank you so much, Tom, for laying out the science and technology behind geothermal. You really gave us a great 101 on how it all works. And now I want to bring in Susanna Dibble, a staff attorney here at ELI, to help us understand a little bit of the regulatory landscape. Susanna and Tom have been engaging with colleagues and partners about how to best catalyze the enabling regulatory environment for geothermal energy, including through a series of webinars and blogs on the future of geothermal. So to get the conversation rolling on the law and policy landscape underlying geothermal and potential developments, I wanted to start by asking you, Susanna, to give us an overview of how geothermal energy is emerging in the US, and, at the risk of using too many puns, who has jurisdiction over this hot topic and its regulation?
Hi, Sebastian. It's great to be here. So as previously mentioned, there are two main buckets when we're talking about geothermal energy. So I'll start with power generation. We're seeing a lot of technological developments, particularly in deep drilling. So when we talk about enhanced geothermal systems or super hot rock, and all of these new technologies are expanding the geographic possibilities for where we can develop geothermal. We're also continuing to see a huge reduction in cost, which is great since that's a huge impediment, just the sheer size of the upfront cost. However, now what we need is more developed regulatory regimes. Historically, in the US, geothermal resources have been primarily developed on federal land, and they've been guided by the Geothermal Steam Act of 1970 with some additional provisions in the Energy Policy Act of 2005. So at this point, pretty old statutes. And so now that we're seeing this expansion of where we can develop geothermal, that it's now a possibility for states all across the US with new technologies, there's a need for better state legislation. And then our other bucket, when we talk about heating and cooling, we're really also continuing to see a growth of particularly thermal energy networks. So when you're connecting multiple buildings using geothermal heat pumps, this has been particularly concentrated on the East Coast. So for example, there's a first pilot project out of Framingham, Massachusetts, but also on college campuses and other regions as well. So lots of exciting developments, but some real questions on how we can then better strengthen the regulatory environment to support even further growth.
And Susanna, to close out the episode, as more states start to grapple with this, what do you see as some of the biggest open questions that are still left to work out?
Yeah, well, as Tom mentioned, we're seeing a lot of new technologies being developed. So I think an initial question is just what of those technologies are going to take off and which specific ones might states want to invest in? And what does that mean for their ability to scale, particularly in states that haven't been exploring conventional geothermal? Financing always comes up as a big question. So hoping that these technologies will bring the cost down, but really how can states find avenues to adequately finance these very large projects? And then I think when we look at regulation, there are questions for states about whether they need to pass new laws, amend existing laws, or even just restructure the agencies that oversee these processes. So I think there's lots of exciting activity to capitalize on and a lot of lessons to be learned from states that have already taken strides to develop geothermal energy.
Thank you, Susanna. That's a great overview to close out this episode. And a big thank you to Tom for walking us through the science behind geothermal, from the conditions needed to generate electricity to the emerging technologies like enhanced geothermal systems that are expanding where geothermal can be developed. And a big thank you to Susanna again for helping us understand a little bit about the regulatory landscape, including how still developing technologies and legal frameworks are shaping the industry's growth. In our next episode, we'll pick up right where we left off. We'll be joined by Caroline de Bossart, Drew Nelson, and Susanna Dibble for a deeper conversation on the financing, legal, and policy questions that will determine how quickly geothermal scales in the US. Thanks for listening to People, Places, Planet, and if you enjoyed this episode, we'd encourage you to share it with a colleague or someone who might enjoy the topic, and subscribe so you don't miss an episode. We'll see you next time.
Thanks for listening to People, Places, Planet, the official podcast of the Environmental Law Institute. Our work wouldn't be possible without the support of people like you. If you'd like to learn more about what we do, attend one of our events, or support our work financially, head to eli.org.